Okay, let's continue the class. Actually, yesterday I recorded the class material, class video 1, 2, and today I'm recording third video. So because I'm busy recently, sometimes I cannot upload the whole videos. So sometimes I can upload part by part. So, but I will promise that I will upload the video at Thursday, and even though it is late, I will finish to upload the video until Friday. So today is Friday, so because our original class time is Thursday. So let's start today's class. Okay, in the last class we learned about the small SO3. The small SO3 is exactly same the skew symmetric matrix. So originally the skew symmetric matrix is generated from the vector. So this vector can be transformed to skew symmetric matrix, and this is used for cross product. So this symbol can be converted to the skew symmetric matrix for more simple calculation of cross product. So by returning to calculate the angular velocity, the third equation here, the third equation is here. This is the equation of angular velocity expressed in fixed frame. So in here, yeah, this equation has the unit vector xyz unit vector, and this is the orthogonality. Yeah, because of the fixed frame is as unit vector, and it follows the rule of our coordinate system. There is a property of unit vector property and orthogonal property. So we can assume this one is SO3, large SO3. And if we define rotation matrix from here, we can convert this equation to like this. When you see this one, actually x hat is a vector. Therefore, this becomes 3 by 3 matrix. Yeah. X, Y, large XY hat is element of 3 by 1 vector. Therefore, this matrix becomes 3 by 3. So, and also it has unit vector property and orthogonal property. We can say this one is SO3, large SO3. So we can think this one is rotation matrix, and we can rewrite this one like this. And in here, if we take the bracket here, then it transformed like this, and this equation is become like this. And by following this rule, we can rewrite this equation, and this one is fourth equation. And from second equation, and this one is fifth equation, and there is a fourth equation. So let's rewrite it together. And from second equation and fourth equation, x small x, small y, small z, the time derivative of this one equal the fixed frame, and this one is also same one as rs, and this one is r dot and function of the time, and fourth equation is equal to this one. So we can rewrite this one, and this one is same. So that is this equation. And in here, this can be converted with the fixed frame vector and r. So this one equal r as r. So this equation becomes like this. So omega s bracket x hat, y hat, z hat equal large x, large y, large z r dot. In here, this one was r s, as you can see in here, and this one is same with this one. So this is r s r dot. So it becomes r omega s bracket r s r equal r s r dot, and this equation is here. And this equation, we can rewrite this equation r s omega s from here and r s r, and from this equation it becomes r s omega r s transpose r s r equal r s r dot, and we can divide using this one and this one. So resultantly, r omega s bracket r equal r dot. Therefore, we can think this equation, and this one goes this way and equal r dot r transpose. So as a result, we find out the skew symmetric matrix of r omega s. This one is skew symmetric matrix of omega s. Omega s is angular velocity in fixed frame. So this can be calculated by r dot r transpose. So that is our result. So so this S means the space frame, or space frame, and also fixed frame. So this is the one of the equation we derived. And let's think about the omega b. Omega b is angular velocity expressed in body frame. because this omega vector, body frame vector, can be converted using RSB. This is a rotation matrix from S to B. So this is the change of the frame, change of the reference frame, and we can write this. And here, RSB is simply, we can write R. For the reference, RSB is equal to this one, and RSB is equal R. And what is RS? RS is representing this unit vector of fixed frame itself. So you can think this one is 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. Actually, RS is here. Yeah. So we can simply write this one. So this one is just simply we ignored the RS symbol, RS index, because for the simple explanation or simple expression, we just erased the RS index in here. So the RS equal R. And by bracket, the left side and right side, we can rewrite the equation like this. And here, the R came out here to here. And then we already know R as bracket is R dot R transpose. So it's R dot R transpose. And by multiplying, okay, in here, R omega B R transpose equal R dot R transpose. And by multiplying R transpose here, and by multiplying R here, we can erase this one and this one, and this one and this one. Then omega B bracket equal R transpose R dot. So that is our second equation we derived here. So omega S was the angular velocity in fixed frame, and the symmetric matrix of that is R dot R transpose. But in the case of the omega in body frame, can be calculate the reverse of this equation, reverse direction of this equation. So it can be confused when you remember these two equations, but don't confuse these two equations. And you should memorize these two. So the important thing we learned in this class was firstly omega S, omega B, how to calculate this one. So RS is R dot R transpose, and this one is R transpose R dot. And in here, R equal RSB. And if we know this 3 by 3 matrix, we can get omega S vector also. Because this from here, this is small SO3. Small SO3. So the form of this matrix become like this: 0, 0, 0, something, 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 something. And also this one is same as omega 3, omega S3, omega S2, omega S1, omega S1, omega S2, omega S3, minus, minus, minus. Isn't right? Yeah, that's right. So if we calculate this one, it should have the form of like this, and this is the symmetric and symmetric and symmetric, but the plus minus symbol is different. So from this value we can get omega s. Yeah. So until now we learned about how to calculate the angular velocity. Okay. We can continue the exponential coordinate representation here, but the content of this one is a little bit long to do in this class. So I will do this in the next week. And because we have some extra time, I will introduce about the Python library of modern robotics. I will simply and very briefly introduce about this one. Okay, just search Anaconda in the Google. This one is the software program to manage your Python or some data science program. And actually the Anaconda itself, it is not the program like Python, but this is the management program. So if you install this one, okay, Anaconda, get started. Download Anaconda installer. Just you can install as you want, and then in my case, I installed this one, Python Windows Python 64-bit graphical installer. And after installing this one, you can get this kind of Anaconda Navigator. So if you learn this program, so this one, Anaconda Navigator. So you will get this kind of things. Okay. So this is the management program of these kind of things, these kind of extra program. So this is about the Python Jupyter Notebook and Python Jupyter Lab. And this one is command line tool. And this one is VS Code, Visual Studio Code, or you might heard about the R language. So this is R Studio. So the Anaconda is one of the famous data science management program. So I usually use the Jupyter Notebook. So let's start from here. Then you can use the Python in the website. So in my case, I have the workspace. I have workspace in here. You can make your own workspace in your local hard disk. And this is my local workspace. And let's make new and Python 3. And you can run the Python program in here, and it provides the graphical interface, and you can run the program in cell unit. So this is one cell unit, and if you enter, shift enter, shift plus enter, left shift plus enter, then you can make one more cells. So one cell in one cell you can add several command line. So if you want install modern robotics library, firstly you should install pip install modern robotics like this, and you should press shift enter, then it learn. When it processing, it express the star symbol, and if it finishes the process, the star is converted to some number. And because I already have the modern robotics library, it just express the requirement already satisfied. So if you didn't install this one, you should install this one first, and then you should restart kernel, restart and run all the cells. So I already installed. And if you want use the modern robotics library, just type import modern robotics as mr. This command means we will import. Import means import is same is included in the C language. So in Python we use import, and the modern robotics library was imported as the simple alias as mr. So when you use mr, you can when you use modern robotics library, you can type as mr, and if you do like this, and you should use like this, and so this word can be changed as you want. And okay, in the first time you should know about how to use modern robotics library. So in the case I use the help command. Help okay, help, I forgot. Help like this. Then you can basic help text provided by the modern robotics class. but there is not many information on here. But in this case, you should type like this, dir. Okay, like this, dir, mr, library. Okay, then you can check what kind of function you can use in the modern robotics library. So this one is the function provided by modern robotics library, and also you can use this one. So we learned about the SO3, large SO3 and small SO3. So let's use this function. I will use just MR because for short coding. So and in MR there is function of test if SO3. So let's have help command like this. Then you can get how to use this function. So test if SO3 function is return true if the matrix is SO3. If the matrix is SO3, it returns the true. So let's test about this one. If you make the matrix using numpy, we did not imported numpy in here. So, but in the modern robotics class, there is numpy here. So in the case, we can use like this, mr dot mp dot array. By using array, we can make the matrix. So in here, 1, 2, 3. So this is first row and second row, third row. So if you make like this, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1. And if you make the variable matrix, R matrix like this, yeah, you can check the R value like this. So by using this one, you can check whether it is R SO3 or not. So this one is SO3. So you can check, you can use this function. But if you put the 0 in here like this, then it returns false result because it is not SO3. So this was the very simple examination of modern robotics library usage. So I recommend you to practice this one several times, or you can check some other functions in here. So we learned about the SO3 and small SO3. So this equation, the vector 2 SO3, can also you can check this this function. So this is the some kind of homework, but you don't need to submit. But You should practice your own. And okay, that's it. Let's finish our class. Thank you.